He's on the infotainment side, distributing information to the car. Rick, thank you.
Thank you.
Yep.
All right, thank you very much. As Paul said, I'm from Harman. Harman, if you don't know us, we do a lot of things in professional audio, we do consumer audio, and we are also the largest tier 1 supplier in infotainment. And so infotainment is GPS navigation systems. We also have a significant footprint in audio systems for the vehicle. So if you're buying a BMW, please buy the Harman Kardon upgrade system. If you're buying a Toyota, the JBL, please do that. Our stock price, thank you. So I want to talk about Ethernet in the vehicle. This is something that I've been involved with for the last 5 years. A group of mine has been involved with. And this, really want to start by illustrating what's happening in the vehicle. So let's talk about what's happening in the car. So a couple of years ago, I was actually head of automotive research. I was in Germany. We were showing this demo of this augmented navigation. Augmented navigation is very cool. We have a forward-facing camera. We have the navigation system within tracking where you are, and you're going to actually superimpose the over the image what's happening in the vehicle. So where you're supposed to turn. And so if you're on a complicated roundabout or you're trying to make a turn, it's amazing how much more intuitive this is. And you can either put on the head unit or we even have it running on a heads-up display. So it just runs right in front of you and shows you where you're supposed to turn. So I'm showing this to a car executive. This is a senior executive over electronics. And he turns to his group of minions and says, I want it, I want it, I want this thing in the car, I can't get it. Because he's got a forward-facing camera already. It goes directly point-to-point wired to a active cruise control thing, and he can't get it to us. He just cannot get the signal. So I'll try to remember to come back to what the net result of that was. A couple examples also surround you. If you've never used one of these systems, they're fantastic. You can, the system we have from Harman, you can literally walk around the outside of your car. And so it's really incredible for doing things like parking and checking things out. Active noise control. This is another example. So we have this program where we do active noise control inside the vehicle. This helps you with things like reducing what's called NVH material, which is big, heavy, dampening material made to quiet down the car. So if you can get rid of that, you get rid of weight. And as we said, that's fuel economy. Another example is things like cylinder deactivation. So if you guys know you've got cylinders, and a common way to improve fuel efficiency is to deactivate cylinders if you're at a constant speed. Well, it turns out they only do cylinder deactivation in a small portion of the range they could. Why is that? Because it just sounds horrible. It's horrible knocking noises and things. So the car makers don't do the full range of this. So we have systems that do cylinder deactivation detection. We cancel out that noise. That's the good news. The bad news is, guess how they run? Basically open loop. They have a microphone in there trying to sense what's happening. So we've tried forever to get a signal from the engine control unit that says, I'm about to deactivate a signal. Then, I mean, as a DSP guy, it's great. It's you're non-stochastic now. I can actually know when something's going to happen before it does, pre-adapt, and really improve this noise cancellation. Anyone guess if I can get a signal from the engine control unit over to me to tell me it's about to do that? No chance. No chance. So, and green in general drives innovation. So we have eco-driving things to help bring down the fuel efficiency. Also, electric vehicles have a lot of concerns about range anxiety. And so people are putting things in to help monitor things. So what's this all mean? Everything that's interesting you want to do in the vehicle requires more and more sensors, and it requires you to have this cross-domain communication that's just, frankly, not possible. And so you need to bring a way for all these things to work together in a way that hasn't been done before. So what we've been doing is working inside of IEEE on the AV protocols, adapting these for automotive, and I'll talk briefly about those and how they fulfill those needs. So first thing is, it's good for when you're dealing in sensors and audio video, for everyone to know what time it is. So we have the 802.1as standard, and the 1722 provides you with presentation time. So if I send audio out onto the network, then every node knows how to be synchronized, as well as you have this idea of presentation time, so when to play a packet. So this is made initially for doing audio-video rendering. You can imagine in a control system, if I wanted to tell you that cylinder deactivation, now I can actually tell you a control packet that says, I'm going to do it in this point now. So there's some very interesting other applications that people are imagining taking these first mechanisms. Other one, in networking, just like in the real world, traffic jams cause problems. So we have QAT, which is a bandwidth reservation. So when you're actually trying to send audio video data from what we call a talker to a listener, you can reserve the bandwidth all the way through the path. So you know that you've got that bandwidth. It's yours for the life of the connection. What's nice is regular traffic that doesn't need to get there very fast, it just fits into the other portion. So you reserve up to 75% of any one link, and anything else going through, if I just need to send some general status or things like that, that'll just happen automatically in the background. The TCP/IP enables algorithm will just make it work. You don't really notice that it's coming a little bit later. But that audio, video, or control traffic, that's given the highest priority. We also have queuing and forwarding rules. So again, think of the highway analogy. If everyone's moving at the same speed, it's amazing how fast you can go. If people are doing different speeds, then you get this bunching and this kind of stuff. They study in traffic rules in the highway. We see it in networking. So if you've got this data that's coming at a regular rate, instead of just bursting it out, you actually pace it out. And then you fit in all your other stuff just in between. You just keep your audio video coming at a regular rate. And by doing that, all the traffic just flows through the network much faster. So by doing this, we can bound latency from point A to point B. If you've got a bounded latency, there's a lot of things you can do already. But we want to do more. We want to do this converged backbone. We want to bring together all the systems into one network. Get rid of all the wiring. So this is where ADB Gen 2, so ADB, the first standards I mentioned, those are already ratified, and those are already in works. We have this new initiative called time-sensitive networking. So think beyond just audio video. Think again about all these control signals we want to send around. So the main aspects, scheduled queues, packet preemption, redundancy, and then a faster time sync. I'm going to go really fast through these because we're short on time. So if you're trying to send data and you want to really minimize the latency through there, then you want this time-aware shaper as it's transmitting out. And what you're worried about is a frame being in there, and I've got this high priority traffic that has to go through. So if I'm trying to do drive-by wire, I'm trying to do automatic braking, it's overall the same backbone, I got to make sure that that signal gets through. So typically you have this guard band where you're kind of waiting, like, did I receive this high priority thing? I need to send it right out. So that's a good idea, but unfortunately the guard band, that's kind of introducing latency and inefficiency. So to reduce that, we're adding even packet preemption. So if you think about the idea of I can have a big packet coming through, and I can actually stop it, preempt it, send the high priority traffic through, and then resume sending the big packet through. Again, for a lot of stuff traveling through the network, that'll be fine. You'll never notice that it was stopped or paused because it's not critical to get through in a timely fashion. But for those really high critical functions, which is where FlexRay that Dave mentioned was developed for, those can get through and we have a very ultra low latency. Multi-path redundancy, there's no way to really have redundancy in the vehicle right now on the existing networks. So having a standardized approach to redundancy allows you to think about this. The GM guys talk to me about, they always like to have what they call a limp home mode. So if things fail, you can still drive the car, drive it to a service station, things like this. And so while they're thinking about reducing cables, taking them out, when you say, you could have a second redundant network here for the absolute critical functions, that's a huge benefit to them. That's something they couldn't do before. When you think about automatic driving, braking assist, things like that, you think about how do I make those systems ultra reliable. Security, we'll touch on it just basically. In general, cars are very easy to hack. They've done security through obscurity. If you see this is from the Forbes article. They took over everything in this Prius. They controlled the braking, they controlled the steering, they controlled everything. Now they were on the CAN bus. However, plenty of researchers have shown how easy it is to compromise a node, whether it's through the OnStar network, through Bluetooth, through Wi-Fi. And so once you're on the CAN network, you've got the whole thing. So the problem is, this CAN network, it's easily reverse engineered, it's easily spoofed. I have personally been inside of government laboratories from 2 different governments, and they reverse engineer cars in a matter of a week. These security researchers who have never looked at a car network before, it took them all of 3 months. So think about a car, unlike an IT network, physical access is actually relatively easy if you want to reverse engineer a particular model. So I could just buy a car, put it in my garage, I got the time. And this problem, though, it's already been solved. There's no way to fix the CAN network, I can tell you that. There's no way to fix the FlexRay network to add on security. However, in Ethernet, we've got standards approaches. They're widely available, they've been standardized, you can bring them into the vehicle. So, a quick note on Avenue. How am I doing on time there? Man, I'm rocking. All right, so Avenue is the organization that is bringing these technologies to industry. So as you guys know, that IEEE develops the standards, then it's up to industry to decide all the things that are in the standards, coulds and shoulds, have to become mights and shalls, numbers that have ranges, particular industries decide on the values of those, and so that's where Avenue comes in. So we have 3 market focuses. It's consumer electronics, automotive, and professional. And so for the purpose of this, so it's good having these guys before me because we're there down there at the RAG-PHY layer, that's not where Avenue focuses. We're up in those next layers of typical .1 work. And so we're really from a standardized Avenue API layer for how you control this. How you control it, we don't really care. But then inside of that, we deal about connection management, network management, the actual transport over those AV networks, bandwidth management. That's where Avenue does its work. This works like you would expect from other organizations, whether it's Wi-Fi or other alliances like this. We have a marketing work group that develops requirements for each of our main market focus areas, and then that goes into certification. And so you've got a pro level certification, automotive certification, and the money we spend on this with our volunteers who take their time, plus the actual contracted work, we're spending millions of dollars on certification and interoperability, and it makes it so that OEMs can have a standardized approach. They can say, develop Avenue automotive certification, D1.1, and all you tier ones bring that. Just a future outlook then of Rick's version of what happens. So this is an image courtesy of GM. If you're talking about going to self-driving cars, what kind of things are we talking about? It turns out that as humans and animals, we've got these great things of sensors of ears and eyes, and we do really well looking, near things close to us, far away from us. We're really well adapted to do things like driving, that was our original evolutionary purpose. To develop a car that does this automatically, long-range sensors, short-range sensors, things that look in front of you, things that look behind you. So the amount of bandwidth we're talking about here is exploding to get to this self-driving car. And even before you hit fully autonomous, just things like enhanced braking, lane departure warning, self-correcting, those things reduce accidents, they save lives. So there's a high interest from customers, high interest from consumers. We can reduce traffic fatalities with these technologies. So all those bring in a lot of bandwidth, bring a lot of new sensors, bring in a lot of cross-domain communications. So what's going to happen? I can tell you, every major OEM is working on Ethernet right now. You know, the conference that we had in Germany recently was close to 500 people that were there, every major OEM represented around the globe. Systems will be introduced in waves. Cars are not done as one complete change, because that's, you know, it's monstrous. So you have different subsystems, and they migrate through with their own lifespan, and they go through the car of a particular OEM. So we'll migrate subsystem by subsystem, but we will see this kind of big growth that Steve was talking about. And that's my presentation. Thank you.